So the next topic is starting of three-phase induction motors. Right, so induction motor starting methods. So why do we need a starting method, or why do we not just connect a motor to something in order to get it started, right? So what we usually have is we say that at the moment of starting, the speed of the motor, the speed of the rotor is equal to 0, okay? And within our equivalent circuit, yeah, we had the resistance at the stator side or the rotor side being given by R2 over S, right? So now if the motor speed is equal to 0, yeah, what will be S? S will be equal to NS minus N over NS, and in this case it will be NS minus 0 over NS, which will give you 1, right? So that is the situation at the start of the motor, when you are just first connecting the power supply. So that means that our resistance within the stator, the equivalent resistance within the stator, is equal to R2 over 1, or simply R2, okay? This is very key, yeah, because this was representing the amount of air gap power that was moving across, right? So that one is all the air gap power is moving to the other side. The slip is 1, so this value is what is being passed through in the rotor. So that means that the current that is within the rotor, yeah, is much, much higher than the magnetizing current. Remember, our equivalent circuit looked something like this. Okay, where we had R1, X1, X2, R2 over S, XM, and R, sorry, the other way around. R core and XM. And remember, we transferred the R core to the other side because we usually lump them together with the windage and friction losses that we go to, we put on the other side. So our current I2 here, this is I1, and this is IM. Our current I2, because this has now become very small, yeah, the value of S is usually very small, 0.4 roughly, which makes this go up. But if it is 1, it means that its value is quite low. It is divided by something, which is actually 0.04 or 4%. So it tends to be R2. So that means that I2 is much, much greater. A greater percentage of I1 will flow through this side than will flow through IM, because your magnetizing forces are the same. But at starting, S is very large, so it means this one will tend to be, it is dividing this into a lower number, okay? So that is the genesis of why we say we need a starting method. At the starting point, S is very high. Therefore, the current that is flowing through will tend to also be quite high, okay? And that is the means by which. Now, at this particular point, we have a starting torque. And previously, we had talked of torque being equal to 3 times omega times I squared 2 over S. Okay, we had given such an amount. Therefore, starting torque TS will be given as omega at starting I squared starting times R2 over S. Now, S at starting is equal to 1, so you can erase that. So that gives you the value of your starting torque. Whereas, on the other hand, full load torque is given by, TFL is equal to 3 over omega S. Actually, this is synchronous, not starting, times IFL, not IS, FL, times R2 over the slip at full load, whether it's 4% or whatever it is. So what is the ratio of the torque? What is the comparison between the torque when you are starting the motor and the torque when it eventually reaches its full load speed? So let's give the ratio of that, TS over TFL. TFL, the ratio of the two, it is 3 over omega S I S squared 2 over T 3 over omega S I FL squared 2 over SFL. Okay. And the elements that will now cancel out, you have that canceling out, and you have that canceling out, which then gives us IS squared over IFL squared times 1 over SFL, which we can write as IS over IFL. Sorry, let me write that a bit better. IS over IFL squared times 1 over SFL will give you SFL. Okay, so the ratio of the torques, the starting torque to the full load torque, is proportional to the square of the ratio between starting current and full load current, right? Times the value of the slip that is there, okay? So let's say that the ratio of starting current over full load current, which is a common assumption, is say 5 to 6%, okay? Let's take it as actually 5 times, not 5%, 5 times, right? 5x, right? And we have been talking of a normal slip of around 4%. That will mean that in an average situation or a typical situation, you have, I keep writing I, you have starting torque over full load torque having the ratio of IS over IFL. We've given it as 5 times. So let's say 5 times a 4%, which is 0.04. That means that the ratio of the two is 1, right? In a normal, typical situation. So actually, the starting torque and the full load torque tend to be very similar. This will become useful as we go along, okay? So these are now preliminary, physical characteristics of the starting situation, yeah? At the point of starting, what does the circuit look like and how does it compare to typical operation, yeah? So now we have established that this ratio between the two, IS over IFL, is very high, yeah? You have 5 times the amount of current typically as you would during normal operation. Excuse me. So during normal operation, what would happen? Yeah, you would have, if in normal operation, let's say full load, if your motor takes, say, 60 amps, it would mean that at starting, you would then have 5 times that. So your starting current would be equal to 300 amps, all right? That's a massive, massive amount of current. This brings practical problems in the sense that if during operation, 99% of the time, you only require 60 amps, that means that the cables that you need to carry 60 amps are a certain size, yeah? Your core cables of the 3 phases, you need a certain size for 60 amps, okay? If you require the same cables to carry 300 amps, they are likely to melt, okay? So what do? Yeah, you would then be in a problem that you would have to have huge cables that would be big enough to carry 300 amps, whereas 99% of the time, you only need them to carry 60 amps. Practically, that's a waste of resources, isn't it? You have tiny cables that are needed, but just because of the starting current, you know, at this particular instant, you need to have cables that are this big. So what do? The aim of starting methods within 3-phase motors with respect to 3-phase induction motors aims to reduce the current at starting to a level that is manageable. So let's have a look at 3 of these methods of starting. Okay, I said we will look at 3, and we'll look at the 4th one as we move along. So number 1, first method we look at is direct on line. In industry, you will then hear of DOL, right? You will talk of a DOL starter method, okay? And this will then look like you will have your motor, let's call it that, and it will be connected like so, okay? You will have a voltage applied directly and a starting current applied directly to your motor, okay? Here in this case, as typical, you would have IS over IFL being equal to 5, and it will lead to what we had talked of before, TS over TFL is equal to 1. So your starting torque is roughly equal to your full load torque. However, your starting current is 5 times your full load torque. Now, believe it or not, there are some applications where this is not a problem. So 60 amps, 300 amps is not a problem, yeah? This is usually in small or low rated machinery, okay? These are the areas where we would make use of that. So we say low rated motors. So the second method is stator impedance starting. I'm keeping an eye on the time. We still have 20 minutes. I think we will still make it. Okay. So stator impedance starting. Sorry. Right. So with this method, you have, similar to what we had done before, you have your motor, and it has its supply. Okay. But in this case, we apply an impedance before the motor and between the motor and the supply, right? So you have a voltage that is the main supply that is put into the motor, and there's a voltage drop across, a potential drop, and then you have a different voltage V2 reaching the motor, right? So what we have essentially, the motor circuit, if I can simplify it, one phase of the circuit will look like per phase will look like that, whereby this is the motor impedance and this is your impedance that you're applying on the stator, and this is your supply voltage, okay? This is V2, right? So what will happen is your V will be equal to V1, which is a voltage that is across the impedance that you have introduced, sorry, not equals, plus a another voltage, which is the load voltage, what is seen by the motor, right? Therefore, your voltage that is seen by the motor is reduced by a certain ratio X. It's a reduction of the supply voltage by a certain ratio X. So this X, you determine it by changing the value of the impedance that you're putting into the motor, right? So this is your supply, this is your impedance, and this is your motor. And we said what the motor sees is a ratio X times the voltage that is applied. So how does that change our motor? All right. Now, the input current, I, that is the input, is the same that will go through to the motor. The only difference is here on direct online, we had an IS that was directly coming from the voltage. The only load in the circuit is the voltage that is there. Just checking. Okay, the only load is the motor. Here with stator impedance, we are introducing a load that gives you a reduction in the voltage. Consequently, the current itself will also be reduced by the same ratio of X, all right? So what this means is that if we look at our ratios again, you will find that TS over TFL is equal to, we said it is the starting current, which we will call XIS, over the full load current, which is IFL squared times SFL. The difference between these two, this ratio here and this ratio down here, is that you are now introducing an X, which is X squared times IS over IFL, which we had before, times SFL. Okay. Now remember, IS, if we assume it is the same motor, the IS purely from the motor itself over IFL was giving us a value, all this was giving us a value of 1. So that means that the ratio between TS and TFL is reduced by a value X, right? X squared, okay? And this is a kind of a transformer ratio, okay? Now, let's look at it from a different point of view. Our IS, yeah, taking into account what we've talked of above here, is equal to, IS is this current, is equal to XV over Z S, which is this one, okay? Or let's call it Z, right? That particular case, okay, the ZS will be changing, sorry, this is not actually. I've confused that. Actually, this one was correct. So we have the ratio TS over TFL being changed by the square of the ratio of voltage that is seen by the motor and voltage that is supplied into the motor, all right? So this means that TS starting torque is equal to X squared times TFL. So it is a very small starting torque compared to the full load torque. Yeah, so one thing about the stator impedance is that you are starting torque is very small compared to full load torque. And at the same time, remember that this is an impedance, right? An impedance leads to power loss. You are literally changing the current. You are dropping the current because you want to reduce the voltage. So at the same time that you're dropping the voltage, you also drop the current. So you have power losses due to this method. Okay, so those are the disadvantages of that particular method. The question here, won't we have a long starting period of the motor? Yes, yes, yes. You do have a long starting period of the motor because the motor takes time to attain its full speed. So yes, you will have, actually that's one of the points that you will need to indicate the starting time. Okay. And one of the other things that you will need to note is it will be important to switch out these impedances once you have reached your normal full load speed, your rated speed, all right? And bear in mind that because you have reduced starting torque, you cannot also run the full load that the motor is able to operate. So it means that you would have to start the motor separately, decoupled from its load, let it attain its speed, you disconnect the impedances so that it is running now at normal rated current, and then you connect your load. Okay. So the final one that we will be looking at is number 3, auto transformer starting. Okay. So in this case, it is similar to what we've looked at over here. We are trying to reduce the voltage that is being given to the motor during start. But one of the best ways of course, doing that is to make use of an auto transformer. So what you will end up with is you have an auto transformer that will supply, sorry, let me draw that correctly, that will supply your machine. Just for clarity. Okay. So similarly, what we have is your auto transformer. We all know how an auto transformer works. It will be having a V, which is the primary, and you will be having an XV, which is your secondary, right? Now, there is the conversion or the transformation ratio, which in this case is given by X, right? So the voltage in the primary will be V, and the voltage in the secondary will be XV, okay? What about the current? The current, IS, in the line is IS, but on the other side, you will have an IS taken to the motor, which on the other hand will increase, all right? Remember, you have a transformation ratio. The power that is moving across the transformer will be changed, yeah? So your IS is equal to XV over ZSC, which is the value of the impedance of that particular motor, okay? So what's the ratio of torque that we had looked at before? So TS over TFL is given by what? It is X times ISC, which is the amount that we have talked of there, over IFL, okay, squared times SFL, right? Now, the IS of the motor, did I call it ISC up here? I didn't call it ISC, I called it IS. Now, the IS in the primary, which is the line current, is equivalent to X times IS of the motor, right? Okay. Therefore, the current is the line current is reduced by a ratio of X. And there is now the advantage that we have our torque being reduced by that, or rather, sorry, that's a disadvantage of your torque being reduced by that. Sorry. SFL. So you have the characteristics of this is line current reduces by a ratio of X. Secondly, one other advantage is you do not have the same heat losses. So no heat losses. And thirdly, we now have the disadvantage that you now have to have a transformer, which is quite expensive, okay, which we in turn have to trade off. That is the trade-off of the transformer usage that we are talking about, okay? So those are the three main methods of starting your three-phase induction motor, right? There are various advantages and disadvantages. Your direct online is simple, but it cannot work with large motors. Your impedance starting is a bit better, but you have power losses. Your auto transformer starting, you remove the power losses, but you have an expensive and bulky transformer, which may not be applicable in a lot of situations. You may not have space, or you cannot have the budget. You might not have the budget of putting in a transformer. Okay. So let's move on to the star delta method of starting induction motors. Now, on screen, you can see two configurations. So you have the star configuration and the delta configuration. Assuming that these are the same motors, that is, we have the same windings, same sets of windings, but configured in two different configurations, the star and the delta, okay? Now, in the case of a delta configuration, you have the windings connected in the delta configuration next to each other, and the voltage that is applied, so the line voltage will be equal to the voltage across the phase. And similarly, consequently, on the star side, the voltage that is applied on the line is different from the phase voltage, which is denoted by this. So in this case, VBR is a line voltage, VBR is a line voltage here, but phase voltages are defined by a single letter. And we'll be looking specifically at this winding denoted by ZB, which is the impedance of that particular winding for purposes of our discussion. Also, one key thing to note, the star winding, the current that is flowing in the line is the same current flowing in the phase, but in the delta winding, the current flowing in the line is different from the current flowing into the phase, okay? So to start with, let's look at what happens if you start the machine with a delta configuration. So in the case of a delta configuration, the voltage that would be applied to each individual winding would be VBR, but the current flowing through it would be some phase voltage IP. So in the case of ZB, if we look at it this way, the voltage would be, so VBR is equal to IP times ZB, right? Current times the impedance. But we know that IP is equal to ILD divided by root 3. That is, ILD is much larger than the phase voltage. The line voltage and the phase voltage are related to each other by a factor of root 3. So this means that VBR in this case is equal to ILD over root 3 times ZB. And if we rearrange this, we'll see that ZB is equal to VBR root 3 over ILD. Okay. Now, this is the configuration in delta. This is the situation in a delta configuration. So let's look at the same in a star configuration. So in the case of a star configuration, we are looking at two things that remain the same. The line voltage remains the same, and your impedance ZB also remains the same for both cases. However, we will allow the currents to be different. So in this case, if we look at our VBR here for the star configuration, VBR is different from VB. So that means that the current that is being applied to ZB is equal to VB. So VB is equal to ZB times I. In this case, our current ST, that is the star current that is flowing due to the star configuration and the voltage applied to it. But we know that VB is equal to VBR over root 3. So let's substitute that back into that one. So we'll see that VBR over root 3 is equal to ZB times IST. If we reconfigure it, making ZB the subject, we'll have we'll have VBR over root 3 divided by IST, right? So now let's relate these two to each other because we have the same ZB on each of them. So we'll have VBR over root 3 IST is equal to VBR root 3 over ILD, right? So these are relating the star current with the delta current. So in this case, VBR cancels out, and we will see that if we rearrange the two, IST will be equal to ILD over root 3 times root 3, which is equal to ILD over 3. So that means that the star current is 1/3 the magnitude of the delta current. So simply by changing the configuration, we have the same voltage and the same machine being applied, or rather that voltage being applied to the same machine. But because you have a delta current, a delta configuration, you will have the delta current being 3 times as much as the star current. So if we were to apply the machine, to run the machine with a star configuration, we would have 1/3 as much current flowing through it as if we would have on a delta configuration. So we would ask, why in that case, if current is much less in the star configuration, why not run it in star all through? The reason for that is, of course, you would not be able to get the full voltage across the windings. You want to have the windings running at the voltage that is indicated, that is the rated voltage that you would have for across the windings as you would do in a delta configuration. In the star configuration, of course, VB here would be 1/3 of the VBR, and that's why you run it at that configuration. So now let's look at how the starter would be implemented practically in a real world situation. So this is the circuit for a star delta starter, right? And when you are applying, or when you are practically implementing a star delta starter, this is the configuration that you would have. On the left hand side, we have the actual electrical diagram, which indicates the way the motor will be wound. And on the right hand side, you have the logic diagram, which is given by, and on the right hand side, we have the logic diagram, which is shown by the way you would connect the contactors for the same. So these individual elements are contactors and coils. Yeah, the coils and the switches that are associated with each of them. So let's go through what this diagram represents. Okay. So here you have the motor, of course, represented by that diagram, by that element. And we have three sets of switches or contactors which are connected to the motor, and these control the operation of the motor. Q1 here, this would be your main connector or your main breaker. You have F1 as your thermal overload in case of any breach or break of the in case of any overloading in terms of thermals or exceeding the temperature that is allowed for the motor, in case of any breach of the temperature conditions that are allowed for the motor, these breakers are designed to disconnect the motor. They offer protection for the motor, right? So now let's look at the logic. So the first step is to depress or press the start button, which is S1 here. And if you look at the, the diagram, the start button is pressed S1. Once you press the start button, you have energized the whole entire logic circuit. All right. So what happens when you energize the entire circuit? First, on this branch, this S2 and this F1 are normally closed. We'll come to those a bit later, but they remain closed. And first, you energize the main coil, KM1 is energized, and KT1 is also energized, and also KM1 in this other branch are all energized. All right. So KM1 is the main coil. So this coil actuates the main contactor here, and the main contactor here, and KM2 is the star coil. So it, when it is energized, actuates the normally open contacts here, and they become closed so that you have a star configuration. Notice that the star configuration simply shorts out the terminals. That means each of the windings, the three sets of windings, are connected to each other at the same, what you call, star point. And finally, once you depress that button, you have KT1 here, which is a coil that starts a timer that will eventually, after counting a certain suitable amount of time, switch itself on. And when it switches itself on, it will activate KT1 over here. We will not yet come to that at the moment. We are still looking at what happens at this first instance. KM2, KM3, this line here is disconnected from the logic at this point. All right. One other consequence of pressing the start button, which is step 1, is that this KM1 will actuate this switch KM1, and it acts as a latch. So it latches on. Even if you release the start button, this arm or this branch of the circuit will remain closed as long as KM1 is closed. Because of the latch action, it is a self-perpetuating loop. All right. So at the first instant, once you've pressed your start, the main contact comes on, the star contact is also connected, and your timer starts. All right. So that's the first phase. We have now energized our machine into a star configuration, which is what we said. It has a lower 1/3 of the current of the delta configuration. However, the voltage is similarly also less across each of the windings. Right. So now step 2 is the timer KT1 runs out its time, say 30 seconds or 1 minute or whatever it is, at which point it will then switch this one to the second position. So at this second position, it disconnects KM2, all right, and it connects this line, all right. That branch is now connected, okay. So KM2 is disconnected. This becomes normally closed as it was before. And KM3 is now connected, and it opens that one, which we had seen before. But the main consequence of KM3 now being connected is that you have KM3 on this other side also being connected. So here we have now switched off the star contact and we have now switched on the delta contact, so that now your motor is connected in a delta configuration. You can see W2 loops back and connects to U1, and then U2 loops back and connects to V1, and V2 loops back and connects to W1. So it's connected in a delta configuration. Okay. Timer has changed. It will continue to be remaining on that side. KM1 is continuously, so that is the situation in the delta phase. And finally, if we wanted to stop, we would press the stop button here, which disconnects this entire branch of the logic circuit, de-energizing all of these coils here, and it disconnects all the main contacts, disconnects the latch, disconnects all the other things, and you have de-energized the entire circuit. So that is how your star delta connector or star delta starter is used to start induction motors.